I'm David Marshall with the Fraser Basin Council, and welcome tonight. It's great to see such a great turnout for a public talk on what's climate got to do with it. And you're going to hear all about that in a few minutes. But just before we get started, just a couple of things. We'd like to acknowledge some of our local government people that are with us this evening. Karen Goodings from the Peace River Regional District, Cheryl Schumann, and Shaylee Wilbur from Dawson Creek. And I gather maybe the mayor of Hudson's Hope may be coming, Gwen Johansson. Fort St. John sends its regrets. They'd love to be here, but they're in the middle of a community forum this evening. I was going to say a few words at the opening of that. Mayor Ackerman. I should just mention, first of all, what the Fraser Basin Council is and what it's doing in northeastern BC. Just a quick show of hands, how many of you have ever heard of the Fraser Basin Council? Great, well, more than I thought, that's good. We're a not-for-profit organization that's been around for over 20 years. And our original focus was on the Fraser River system, but in 2009, we expanded to go province-wide. Because primarily we're involved in a number of different issues that are of interest to the entire province, such as climate change, water management issues, and sustainable communities. And of course, those cover an awful lot of different issues. And we first started getting active in the Northeast, probably about 8 or 9 years ago, I guess, Karen, with the human health risk assessment, when we were doing some work with the Ministry of Health and looking at the human health risks associated with oil and gas development. Then over the years, we've helped some of the communities, the regional district, and Hudson's Hope, Dawson Creek with some strategic planning. And then we've done water management workshops. And then last March, through the BC Regional Collaborative, Adaptation Collaborative, we convened a workshop here in Fort St. John on floods and drought. And we invited the Federation of Canadian Municipalities to come. And there was a lot of really good presentations on impacts on communities around wildfires and flooding. And so they were quite struck by that, and they introduced a program around climate adaptation and suggested that we probably should apply for that. And how it works is a not-for-profit needs to find at least 5 municipal partners and then make a submission. And so we went around and approached a number of municipalities. And so the Northern Rockies Municipality, Regional Municipality, Dawson Creek, Fort St. John, Tumbler Ridge, Chetwynd, Goose Coupe joined with us, and we submitted an application to the Federation of Canadian Municipalities, and we were fortunate to be the only application from British Columbia to get accepted. And so we then got some support from the provincial government, from the Ministry of Municipal Affairs and Housing, and the Ministry of Environment and Climate Change Strategy. And then the 6 municipalities also put in some financial support as well. So we have lots of funds over the next 2 years to focus on 2 things. One is to look at a regional assessment for the entire Northeast, which will help us inform community adaptation plans for those 6 communities. And eventually our plan is that we'll expand the network once we get rolling to invite the other communities that have expressed an interest but weren't able to join at this time, and extend that to First Nations communities and other interests in the Northeast, to hopefully have that as an opportunity to share information as we deal with resilience issues, especially impacting our pressing infrastructure. And the mayor of Hudson's Hope just joined us, Gwen Johansson. Good to see you here with us. Great. So without further activity on my part, I'd like to introduce the team that's with us tonight. With my staff, Roland Chia, who some of you have met already, and Kate Murphy. And then with the Ministry of Environment and Climate Change Strategy, Amanda Broad, here she is. And then Michelle Connolly with the Pacific Institute for Climate Solutions. They're also a partner with us. She works with the University of Northern British Columbia. And Jillian Abu-Bynes is going to be a consultant working with us over the next 2 years. But it's my pleasure at this time to introduce our guest speaker for this evening. That's Trevor Murdock, and you'll see a short bio in the description that was given to you as you came in. But I'd just like to spend a little bit more time introducing Trevor, because we're really pleased to have him with us this evening. He's a climate scientist with an undergraduate degree in physics and astronomy from the University of Victoria, and a Master of Science in Earth and Ocean Sciences from the University of Victoria. He currently leads the Regional Climate Impacts team at the Pacific Climate Impacts Consortium. For the past 20 years, he's worked on applications of climate research to assist decision-making and planning. His work is focused on climate scenarios and online mapping tools, downscaling to high resolution, analysis of historical climate data, and improvement of seasonal climate predictions. His current interests include use of climate projections at the community level, impacts of climate change and biodiversity, and analysis of results from regional climate models and other forms of downscaling. Please welcome Trevor Murdock.
Thank you, and thanks to everyone for coming out on an evening to hear about climate change. So one thing I want to start with is that I'm going to be trying to be fairly interactive, and so I've got this poll EV. So anyone who has phones or computers, laptops with you, you can go to pollev.com/climatepkick288. There's going to be a bunch of questions. There's free Wi-Fi in this room, and the first question is going to be this one. So it's actually Northern Grand Hotel, and then password Northern Grand. So the first question is, what elements of the climate system do you see in this photo? And the idea, okay, I have to turn this on. So the idea is that this won't replace actual conversation. So if you don't have a phone with you, feel free to shout out. But this is also meant for those folks who don't necessarily want to shout out their answers in front of everyone. You can submit your answers this way. So it should be on. Has anyone tried yet? So this is the poll. Oh, here we go. Sun, trees, vegetation, soil. Oh, right, you can't see the photo. So someone with a good memory could see it, but so anything else that you see in this photo, an element of the, and this is set up as a word cloud, so if you do one word at a time, that's going to work out the best. Drought, yeah, that's something that's going on here. I'm really kind of looking for what's like physically the part of the climate system, so things like vegetation, which we saw on the previous slide. Flowers. I don't know if I can see the answers at the same time. That's the hard part. Clouds, a lot of people saying clouds, sun, tree, atmosphere, yeah. And then often, I don't know if anybody mentioned mountains, so this maybe, BC has complex topography, even up here, maybe less so here than in other parts of BC. But this topography is still important here. And of course the ocean. Did anyone mention the ocean? The ocean is a big one. All right, well, so this thing is working, and you can keep answering that if you like as we go on. But I'll move on to the next slide. So just in terms of what we'll be talking about, I'm going to start off by just talking about what the last 3 years have been like in terms of weather events, and asking folks to, asking you to, tell the room about what's been going on, and that we'll use this interactive thing for that. And then I'll talk about weather, climate, and variability, and then we'll get into preparing for the future, preparing for climate change. And some nutrition facts for those of you who, some of you have already had some food, but this is in the next 50 minutes. I've got almost 50 slides and an overdose of maps. I'm going to be showing a lot of maps and not a lot of photos. Unfortunately, you've already seen a quarter of the photos in the whole thing. And if you didn't find this funny, then that 5% humor is off as well. So just a little bit about PKIC. As was mentioned, I lead this sort of regional climate impacts theme. There's two other themes. We got folks focusing on hydrological impacts, and then climate analysis and monitoring is sort of historical trends, El Nino, La Nina, seasonal predictions, and that sort of thing. We've been around for a little over a decade, and we're a sister organization to Pacific Institute for Climate Solutions, which Michelle is from, and so we have these two organizations with almost the same name. I like to say we're the nerdy sister. We focus on the physical climate 50, 100 years from now. PICS has to focus on the hard part, which is policy and how to, what do we do about reducing climate change. So we're focused on the applications. And as I mentioned, I want to start with what has gone on in the last few years. So this I've just taken from the event description. So these are some of the things that we're aware of have gone on. If you're interested in BC the last 3 years and how over the province these individual years have compared to how do they fit with in terms of climate change trends, we have sort of an annual series of articles on this, and so you can find those on our website. But I'm going to go to asking everyone this question, so I'm going to switch to turning this on. All right. What was remarkable in this area in the last 3 years in terms of weather events or unusual seasons? And this one, I think, is also a word cloud, so I think single words are going to work better here.
If you want to join words, then you can do that.
Yeah, do an underscore if you really want something that's 2 words. So wildfires, a lot of fires, flood, freezing rain,
Winds,
wind,
high winds.
high winds. Erratic. What was December connected to?
Snow.
December snow, yeah. So this year, right, is a La Nina year, which is colder than normal and wetter than normal usually. So spruce. What happened with spruce? Spruce bark beetle. Yeah. Flash floods. Okay, so I'll leave this up. You can keep adding to it, and we'll come back. Bats. Wow. So are there species in the area that haven't been previously? Is that what that's about? All right, I'll leave that open so you can add to it. But I'll go on to the next slide. So this is just, so a lot of what we just heard about, maybe those are associated with climate change, but a lot of this is also just weather. So how do we sort of sort this out? So just a refresher to remind folks the difference between weather and climate. So this is a real example. On December 2nd, 2005, I was in Montreal at a climate conference. I phoned back to my family in Victoria, and in one of those 2 places, it was 19 degrees and sunny, and in the other one, it was -5 degrees and snowing. So I'm going to switch to this question in a second. Which one was the warmer and sunnier one? A for Victoria, B for Montreal. Okay, so I'll give folks a... It's neck and neck, no. Oh, back, oh, this is a close race. All right. Oh, okay, I guess my sense of humor is kind of obvious. Usually this lands around 50-50 if I pull a room, but... all right, we'll move to the next question. Oh, I'll tell you the answer first. So the answer was Victoria was cold, was sunny. So Montreal was 19 degrees and sunny. That was the answer. So it's usually about 50-50. But I was asking you about the conditions in a particular place at a given location. Unless you have an eidetic memory and we're in one of those 2 places, you wouldn't know. And that's the point. But so that was weather. Climate is the condition over some period of time, some average. So if I were to ask you instead, what is the, I should say what, not where. Oh yeah, no, it should say where. Hold on. Confusing myself by going here. So climate is long-term statistics of weather. If I instead ask you, take every day in December during 1971 to 2000, so 31 days times 30 years, average them all together in these 2 places. And I tell you that one of them is, the average is 4 degrees Celsius and 14 centimeters of snow. The other one is 10 degrees colder and 4 times as much snow, and then ask you which one is which. So that's this question. So where is this averaging of all of these 30 years times 31 days? Which one is 10 degrees warmer with 1/4 as much snow? So a couple people unfamiliar with Canadian geography or know that I would find that funny to answer B. So thank you, or whichever. Yeah, so okay, so most of us know the difference, and now it's going to get worse probably. But so most of us know the difference between climate and weather. By the way, for anyone familiar with Victoria, does that seem high, the 14 centimeters of snow? It seems high for those of us in Victoria. Maybe that doesn't seem high to you guys, but this is a 30-year average, and in a normal year, we don't get 14 centimeters of snow in Victoria, but we had a blizzard of 96 in there, which is like 70 centimeters of snow or something. And so that 1 year being in there really skews the average up. So we're already getting this sense of climate variability. An individual year can make a big difference even in an average like that. So here's the right answers. It was -5 and snowing in Victoria on that particular day, but of course it's 10 degrees warmer and much less snow. Okay, so now we're going to look at the same idea and globally in a bunch of different seasons. And I forgot to mention, by the way, if anyone has any questions like of clarity, please, if something's confusing and I'm just going on, feel free to interrupt me. But if you just sort of want to go deeper on something, maybe just wait, because I'll probably have a question where I'm going to invite comment. So, but don't let me go on if you're getting lost. Okay, so we're looking here at summer of 2003. Don't worry about the exact colors too much, but basically the yellow colors are warmer than normal, normal being 51 to 80 in this case. And the blue colors are colder than normal, and the darker the color, the further away from normal you are. So this is a global map. We can see somewhere vaguely, roughly in the area we are. That asterisk is not perfectly accurate. But we're in this spot here where this summer was warmer than normal. Anyone remember what was going on in BC in 2003? Not in this area so much, but yeah, wildfires. The Kelowna wildfire in particular was the one that really captured the news. And this is not directly caused by this, but the warm summer and wildfires are related. And I've circled this 0.49 up here because that's globally over the entire planet. If you average all these temperatures together, the globe was only about half a degree warmer than normal. There was also in this year, this is when there were tens of thousands of deaths from heat-related illness in France. But the point I really want to make here is that there are spots on the globe that are colder than normal. So even while we were having these wildfires here and the heat-related illness in France, Japan was colder than it's normal in that summer. There's a few other spots in the globe as well. And if you watch as I go through a bunch of these in a row, you'll find that continuing to happen. So here's 7 years later. This was following a La Nina year where spring is usually colder than normal, but in BC, in most of southern BC in particular, it was still colder than normal in July, and we were wondering when will summer ever arrive. But globally, this picture is still almost exactly the same as the last one, so half a degree warmer than normal. We just happen to be here in BC in one of the spots that was colder than normal. There are plenty of places in that summer that were warmer. Russia, for example, was having, again, heat-related illness due to being a lot warmer than normal. And you'll see as we go through. So coming now to the more recent, so we're asking about the last 3 years. So here's winter of 2015. This is now the warmest one we've seen globally, 3/4 of a degree. And this is where we have, in North America, we had much warmer than normal conditions in the west. And this is when we had Snowmageddon headlines back east. And things like, well, climate change must have stopped because it's snowing in where I live. And so that's not the case, right? This is the warmest one we've seen so far. So it's just that spatial variability to climate. Now getting a little bit closer to today. So this is winter 2016. And yeah, we see, so this is now again the warmest one we've seen so far. Almost globally everywhere warmer than normal. There's some spot in Africa there that's a little bit colder than normal. But even in that warmest one we've seen, there was some spots warmer than normal. And again, December, January, February 2017, we saw colder than normal conditions. Again, we are in a La Nina year. This was actually last year, which was also a La Nina year. One of the only places that was colder than normal. And that year, though, the year of 2017, still ended up being about normal, despite the fact that the winter was colder than normal.
How are you defining normal?
So normal here is 51 to 80. So it's just the average at every location in 1951 to 80.
So you don't take into account those warmer days from 1981 to the present in your
Right.
calculation?
That is a good question. So the question is what's normal? And I use that term loosely. Really, there's no such thing as normal. It's a normal period, or a baseline is another term that we use interchangeably. The whole concept of a climate normal, as climate is changing, there really isn't a fixed climate. That's kind of what we're talking about when we're talking about adapting to climate change. We've sort of built our infrastructure and built our cities and wildlife management. All of these things assume a static climate that isn't actually the case. So all of the maps we've looked at here globally, you may notice, they've all been warmer than this 1951 to 80 baseline. And that's because we haven't had a month colder than the 51 to 80 baseline for several decades. You've plenty of places that have months or seasons colder than it's normal, but globally we just haven't had a colder than normal month in several decades. Okay, so what about here? So now focusing in, and now we're looking at this sort of time series, what has happened in the past over the last century, and keeping in mind, so this is a regional average for sort of the Northeast region, keeping in mind there's not a lot of stations in here, so there's a lot of variability, and we're just averaging over a couple of stations. And you can see a couple of things. So we have warming trends. This is something like on the order of 2 degrees per century. Over the century as a whole. The slope of this line, if you started in the middle of the century to now, is steeper. This is would extrapolate out to 3 degrees per century. And you can see we've got Fort St. John and Dawson Creek in there. The individual locations are pretty similar to the regional average. That's for winter nighttime low temperatures. For summer precipitation, also increasing trends. If we looked at other seasons, we may actually find differences in the 100-year trend and the 50-year trends. Last thing I want to say about trends, now this isn't just the Northeast, this is North America as a whole, but just to talk about a little bit about the changes in the extremes. So if you look at all of Northern Hemisphere land temperatures, you get this kind of bell curve, like you're graded on a curve in school. And this is the base period, 1951 to 80. And if you look at the next 3 decades after that, what the temperatures that occurred, you can see the average shifting to the right, but you also see it sort of skewing. So what you end up having is these events back in 1951 to 80 that were warm enough that they occurred at 0.1 to 0.2% of locations. So this is extremely rare to occur in historically. So it's 1 in 100 or 1 in 50 chance. Those occur in 4 to 13% of locations, the same temperatures by 2001 to 2011. So the trends I was showing of a couple of degrees over a century doesn't sound like a big deal, but with a couple of degrees shifting a distribution like this, you can have quite a large impact on how often these extreme events are occurring. And we'll see some of that. We'll look at some indices in a minute that are a little more relevant than just what's the average seasonal temperature, which as humans we don't really have a great sense for what that even means. So to do this, what I'm going to do is I'm going to zoom in, focus on 2015. And this is sort of BC as a whole. In 2015, just the way the numbers worked out, there's this question, is 2015 sort of the new normal? And we'll see that for BC as a whole. So BC, for 2015, was quite a warm year. It was a record-breaking warm year for BC as a whole. Northeast corner of the province was actually one of the few places that wasn't record-breaking hot. It was a warm year, but it wasn't record-breaking warm here. But average over the whole province, it was still record-breaking warm. And associated with that, most places had near-record flows, both high and low. That sounds contradictory. We'll see what that means in a minute. And then soil moisture all-time low and evaporation all-time high. So just to dive into this a little bit. So what we're looking at here, and here's the slew of the onslaught of maps are starting. So what we're looking at with these dots, these blue colors are, this blue color here is the top 10 percentile of spring stream flow. And so you can see very high stream flow across most of the province, including here in March, April, May. If we advance forward to May, June, July, you can see that down in the south coast, they're starting to be flipped all of a sudden from record high flows to record low flows. Not yet here, but not as high as they were. And then here, by July, August, September, record low flows everywhere in the province, basically. So what is going on with that? So this is just to look at somewhere close to here. So Pine River at East Pine, you can see a couple of things. So the blue line is 2015. We're looking at a hydrograph. So this is sort of the calendar year. January's hydrograph through April, July, down to the end of the year. Blue line is 2015, and then all the other squiggly lines there are the last 50 years or so. So you can see a couple things. Much higher stream flow in winter. This basically is the warm temperatures causing what would have normally been snow to arrive as rain. That's basically what's going on. That's why it's such higher stream flow. And then as you move into the spring, you get this kind of lower and earlier peak. So this peak is quite a bit lower than most of these. It's sort of hard to tell, but you can see the distribution of all these. So this is on the low side. Not a record low peak. Many parts of the province had record low peaks. And then through the summer, you can see lower low flow. This looks like it might have been record-breaking low for part of the year. Does that make sense? So to sort of see what precipitation's role is in that, we can look at snowpack. So there's temperature and precipitation together, of course, is what's going on with snowpack. So in 2015, we had, again, this is a different color legend because these come from different places. This also seems out of focus, but maybe that's okay. I'll just explain. These are higher than normal snowpack here, and only the southern part of the province was already low snowpack by April 1st. But by June of 2015, we had record low snowpack everywhere. 2016, on the left-hand side, in April, this is almost the opposite of what we just looked at in 2015, where we had lower than normal snowpack in northern BC and higher than normal snowpack in southern BC. But by June, it didn't matter because it was just warm enough that it didn't matter. So you had more snow to melt in some places than others, but by June, you had record low snowpack. 2017 was real weird because we had a colder than normal start to the year, winter and spring, and then record-breaking hot summer. So we had places, there are some places in southern BC where we had higher than normal snowpack in April 1st, still higher than normal snowpack in June 1st, and yet still drought by end of July because the snow just melted faster than ever and when we had real hot conditions. Still lower than normal snowpack up here. Okay, so now we're going to start talking about the future. So here's a really important question. Get your phones out. Who said this? Okay, it's pretty even split. I'm going to leave it open and I'm going to go here. If you Google this or Wikipedia, you'll get all of these answers. And so my point is that it's hard enough to understand what has happened. Trying to get into predicting the future is even harder. But let's do that. So what we use is these climate models. And so now we're looking at, we've already looked at this kind of stuff for the Northeast. Now we're looking at BC as a whole because it's easier to sort of make these general climate science points with this. So we've got this historical, wiggly, some years are cold, some years are warm. We have 2003 is in here. This is the Kelowna wildfire year. We had these last 3 years we're talking about record-breaking. 2015 and 2016 are on here. If 2017 was on here, it'd actually be pretty close to normal. which is, again, hiding that it's colder than normal in part of the year and warmer than normal in another part. And what we're seeing here, so these are the future projections. This is a future projection under a very optimistic extreme emission reduction scenario. And under this scenario, so to get here, we need to get to zero net emissions, so 100% reduction in our greenhouse gas emissions within a couple decades, and suck carbon out of the atmosphere and stay at zero. There's some debate in the science, this is not the part of climate science that I'm expert in, but there is some debate in the literature about whether this is even attainable. But it's certainly, if it is even attainable, it's very optimistic. And under this scenario, that 2015 and 2016 are actually about the new normal. So under this extreme scenario. We have two other scenarios here. So the red line is sort of a business as usual. It's a little bit better. We often call it that. It's a little better than business as usual because this has us getting to this. Under this scenario, we're still getting to net zero emissions. So by the end of the century. But we're not actually getting to that net zero until the end. So we sort of postpone getting to net zero till sort of as late as possible. We're not currently globally tracking this scenario. We're a little bit worse than it at the moment. But what matters is the total net emissions, not necessarily how we get there. So if we do terrible for a while and then do really good, we could still end up down here or one of these. But if we did follow this particular scenario, which is sort of business as usual-ish, we end up in what I'm saying is a different place. So what I mean by that is if you follow this, we're still going to have climate variability in the future, right? So if you take this sort of wiggly historical record and slide it up in your mind, following the middle of this dark red line. The range around it is uncertainty from two things: uncertainty in climate models because they're not perfect, and it's the natural variability. It's this wiggliness. But if you slide that up here, you'll see that this is the average. The dark part is the average. So we'll still have years that are quite a bit colder than normal, and they'll be about here. Those extreme cold years in the future that are so cold causes weird things to go on in the landscape. You know, all of these extremes throw us for a loop, whether they're on the warm extreme or the cold extreme. Those extremes that throw you for a loop in the end of the century are actually warmer than that record-breaking 2015, 2016. So that's what I mean by being a different place. If what was a record-breaking hot is now the abnormally cold, that's really not a different place. And to get to these kinds of temperatures in BC, you've got to go back tens of thousands of years, possibly millions of years. The paleoclimate record gets dodgy when you go back that far, but potentially millions of years before you have temperatures of that magnitude. So, but what does this mean for planning for climate change? The project that David mentioned at the beginning. The good news is, for planning, we tend to be focused on the middle of the century for adaptation planning. And in the middle of the century, these scenarios are similar. So by the end of the century, you know, if you want to, change the size of stormwater pipes or something like that, or you want to decide what trees to plant or something like that, if you're trying to make a decision that based on the 2100, you really have to make some assumptions, which of these scenarios are we following. But if you're planning for the middle of the century, it's not as big of a deal. You can just plan for one of those or average them together. Most people tend to take the more pessimistic one and plan for that one, and then you're being sort of engineering conservative. You're planning for the sort of worst case of those cases. But the point is they're not too different from each other in the middle of the century. The other important point is that while these are not too different from each other, all of them are different from the past. So when we build a building, a new energy efficient building that we're super proud of, LEED Platinum, but we use the historical building code to do it, we're actually missing something there. We're designing for heating and cooling demands that building is not going to experience if you were to look at the middle of the next century. So what does this mean for other things like hydrology we were talking about? So this is Peace River at Taylor, so it's quite a large basin. But it's the same three things that we saw in the Pine. Higher stream flow in winter because you're getting more precipitation as rain rather than snow. Lower and earlier peak, and this progressively more and more so later in in the 21st century. These three lines are into the 21st century, and then again, lower stream flow in the summer. Basically because you just didn't store as much snow in the winter, so there's less to melt in the summer. Now looking at soil moisture and evaporation, because one of the annoying, I don't know what the right adjective is here, for things about climate impacts is that we can be facing both drought, or both flooding from extreme precipitation and also drought, which seems contradictory again, but isn't. Climate is messy. And so this is just looking at evaporation and soil moisture, these two variables. They tend to go together, that's why you get this thing that goes across these two quadrants. The gray dots are all of the last century. This is BC as a whole, and the difference from normal. So 2015 was out here. 2015 had the record-breaking high evaporation. It makes sense, it had record-breaking high temperature. And it had record-breaking low soil water content. These yellow and red dots are the future. Well, it's 2016 forward, actually, and from one climate model. And you can see relative to that 2015 was on the wet side. So and I'm not sure what it was like here if you had drought conditions in 2015, but again, this is BC as a whole. But again, the sort of idea of, was it a new normal? Not really. It's actually kind of on the cold side of normal and on the wet side of normal.
Have you or any of your colleagues done anything with the wind data?
Wind is tricky. I won't get into it too much other than just to say the climate models that I'm basing this stuff on, they tend to use wind as almost more of an internal variable. So the climate models they're essentially fluid dynamics models. They're solving the motion of fluid on a rotating sphere. And then it gets more complicated after that. There's exchange of heat, and you've got vegetation and chemistry and all this kind of stuff. But wind has been treated by climate modeling groups almost as an internal variable. It's there to make sure you're closing heat budgets, and you're moving the right amounts of things. What people are interested in is wind at the surface, and it's sort of apples and oranges, so it's just tricky. There is some work going on at wind we can talk about maybe afterwards, because like I said, it's not as readily available basically as the temperature and precipitation. And as we'll see, so I've got a couple slides, and then we'll start getting into sort of high resolution temperature and precipitation maps for this area. And unfortunately, we can't quite do that for wind. But we can say something about wind, and we can talk about that later. Okay, so what we're looking at here is, the figures we were just looking at where we had the wiggly variability and then the future projections, and basically just flipping that on their side. So imagine the historical wiggly part flipped on its side, and then this is the width of the historical variability. Does that make sense? So this is the historical variability, averaged over all of the Northeast region. The average temperature is something like minus 16 degrees. This is the 61 to 90 average. So the center of that is here. So what we're showing in the colored bars is where does the center move? Not the whole width, but where does the center move? And there's a range because the climate models are not perfect, and it's kind of impossible to separate all of the variability from it. So there's some variability built in there as well. The point is that we're looking at warming in winter and also warming in summer. But if you compare where this bar moves to the historical variability, there's overlap, even by the end of the century, in the winter temperatures with these extremes. In the summer temperature, we're way off past the variability, partly because the variability is lower. Another way of saying that is, the part where I said there's no overlap by the end of the century, what was a cold year, what is a cold year by the end of the century is warmer than the warm years in the past. That's even more true in the summer than in the winter. So that was based on annual, but it's more pronounced in summer. On the precipitation side, now we're looking at the same thing for precipitation. And again, you can see increases generally in winter precipitation, still at least some overlap with the historical variability. And then in summer, again, because normally there's more precip in summer, the variability itself is larger. So kind of the opposite is true. Increases in both seasons, but the winter and also spring, if I were to show that, increases might be relatively larger, even though the total amounts in millimeters may be less than the summer increases, if that makes sense. We'll see this in another way in a map in a second if it doesn't. Okay, so I just want to mention these two reports that were done by the Fraser Basin Council with the oil and gas sector, with and for the oil and gas sector in the area. So there's a sort of scientific backgrounder and then a summary report, and these are available. You can Google them. And what we're doing now is the project that Dave mentioned at the beginning that Federation of Canadian Municipalities is funding is updating the climate projections with more recent information, and then the important part is the community's talking about what that means to them. And so I'm going to ask you guys what that means to you after I run through this series of slides. Okay, how are we doing for time? When am I supposed to end? I should have thought of that at the beginning. In half an hour? That's right? End at 7:30? Is that right? Somebody tell me.
I know it's 8:04.
Okay. Right, end at 8:30. Okay, I got it. All right, so what we're looking at is annual daytime high temperatures. So this is the past. Don't worry too much about the exact numbers, although it's kind of interesting that, so the colors flip from blue to yellow, where the average annual daytime high temperature is below freezing versus above freezing. So most of the area it's above freezing. You've got some spots up at high elevations that are actually on average below freezing. You can see that by the middle of the century, there are no locations, even these highest elevations, furthest north areas are no longer below freezing on average. And you've got several degrees of warming. What does that actually mean in something in terms of impact? So there's this variable called growing degree days. It's basically, you take every day of the year, how far past 5 degrees Celsius it is, and you add up how far past it. So if it's 10 degrees, that's 5 degree days, because you're 5 degrees past 5. If it's 6 degrees, that's just 1 degree day, because you're 1 degree day past 5 Celsius. And you add all of this up as kind of an indicator of what crops you can grow, basically. And this is something like a 20% increase in the growing degree days on average for most of the area, with more pronounced effects in some areas than others. Same kind of thing, winter nighttime low. So again, as humans, we don't necessarily have a great sense for what does an average winter nighttime low temperature mean. But most of basically the whole area at least is below zero. The average winter nighttime low historically was below zero. You start to see the southernmost parts of the region actually having annual, I'm lying. This is not the, okay, so I showed the change here. So this is, no? Sorry, just a second. These are weird colors. Okay. This is the past, this is the future. Still below zero. So this yellows here is -6, but warmer than -6. And this yellow over here is -9 to -6. Still, several degrees of warming. What does it actually mean in terms of something that's a little more relatable? So this is frost days, number of days below zero in a year. And you can see if you add this up, it's like 6 to 9 months of below zero temperatures, and you go into the 2050s and you're looking at about a month to 2 months less days below zero. That might sound good to some people. Maybe not good for like permafrost or for driving on permafrost roads and things like that. This is another one that might sound good. Summer daytime high temperatures. So we've got the historical on the left and the future on the right. And then translating that into something that's maybe a little more meaningful is the number of days above 25 Celsius. And so this, you can see number of days above 25 Celsius, sort of 20 or less per year on average. And here's where I showed the change. I think the change is more relevant. So it's almost a doubling, perhaps more than a doubling in some places. So a month more days in a lot of areas, with a number of days above 25 Celsius, which again may sound great, but might be weird to actually think of, like heat-related illness being an issue in this area, where that might not have been the case before. Precipitation. So again, spring. So now we're looking at spring and summer precipitation, showing this in terms of percent change. These legends are not quite the same, but actually, if you look at the legends, this legend goes up to 40%. This legend goes up to 20%. So the spring change is relatively larger. But if I showed you the same thing in millimeters, the summer change is actually larger in millimeters, right? Because you get more precip in summer than in spring. But that relative change might be more important. If you look at this in terms of, okay, so who cares about the spring, annual spring, or average spring or summer precipitation, but that 1 in 20 year wet day, so in terms of the extreme precipitation that might cause flooding, you see a larger relative change. I don't have the percent change on there, but this is larger than the seasonal changes themselves. All right, so I've got just a couple of slides here which are links to resources. If you're interested in getting your hands on some of the climate data that's available, I recommend this webinar which Fraser Basin Council organized. And there's just links here to a bunch of different sources of that data. And this will be made available, the slides will be made available to anyone who asks Elena, I guess, for them. And then there's just a links to a bunch of other resources that you may find useful, more about climate change itself, or about folks that have adapted to climate change. So this is my summary of what we've talked about. Unless anyone has any specific sort of clarification questions on this, what I want to spend most of the rest of the time is, I've got 3 questions for all of you as an audience about, so what does what you've just heard mean? Any clarifying questions before I go there? Going once? Okay. So after hearing this, what climate impacts are you concerned about, if any?
Remember the underscore to join.
Yes. Yeah, so this is a word cloud one, so it'll only accept single words. If you don't put an underscore between them, it'll just split them out as if they're separate words. I also should mention there's one of these 3 questions coming up that you can't do if you're texting. So it's going to be better, actually it's the next question. So it is a little better if you use the URL rather than texting. Is there air conditioning here at all? Much right now? Little? Yeah, so the same with the West Coast. Yeah, one thing I didn't show is cooling degree days. That is another, it's like growing degree days. And it is something that we have access to. Higher electricity use. Does anyone want to talk about these? So drought is really important.
Well, I think the wind issue is far more significant than it was showing up there right now.
It's increasing wind you're concerned about? Causing,
And gusting.
and it's extreme wind in particular, yeah.
Your poll is full.
Oh, it's full, okay. It hits max at 50 people, so that's good. Are there 50 of you with, maybe it's 50 responses. All right, so this one you need to, this one doesn't work if you're texting, but that's okay. It's the only question like that. So this is, based on what we just saw, you're gonna have to re-enter an item, but now what you can do is rank them. So which impacts are sort of the highest, which require the highest priority action? Which ones are you really concerned about and would like to see some planning going towards trying to adapt to? And can someone put wind up? Because it was mentioned here. So what is the wind impact? It's the gusts like knocking trees down, or?
Our windmills will stop in a gust.
I see.
And wildfire and winds are a big issue.
The combination of wildfire and wind, yeah. So you can vote, you can vote on each item, but only once. So you can either plus it or minus it. You can thumbs up or thumbs down. And you're not insulting an item by thumbsing it down. You're just saying it's less important, priority-wise. These are all going to be important. This is an interesting one. Reduce fossil fuel use. I guess that is, in some ways, adapting to climate change because it means you have less to adapt to. But we're usually sort of what we're looking here for is which impacts. So wildfire, food. So the growing degree days are maybe good news for food. Although, yeah, if you have more extreme precipitation, that may threaten any advantage you can get from the increased growing season. Not sure why wildfire's there twice.
But famine is down there too, and that would actually go in with food.
Famine would go in with food, yeah.
Can you scroll down so you can see the stuff?
So anyone who's viewing on their phone should be able to see them all. For people who didn't bring their phones with them, Amanda, I'll scroll down.
Just being present.
Yeah, so a couple of these would really combine. And this is just a snapshot of what folks in the room are interested in. So, but I think the people tomorrow will find this interesting. This is the kind of things that we'll be talking about. How do we adapt to these things? Does anyone? Okay, so the next thing is just to start you thinking about it before I move to it. The next thing is what can you do, and what can we do collectively about some of these things. So what are some of the ways we can adapt to these changes? So now what steps can we take to prepare for climate change? Yeah, and so by the way, this one, because I knew there's going to be phrase answers here, it's not a word cloud. Every answer is just going to show up. So you don't have to worry too much about you can use spaces now. It'll be fine. There's a lot of interest in reducing greenhouse gases, individual action. So what about preparing for the impacts that we just saw? Irrigation. I see irrigation and growing your own food. Those are some great examples of what we can do. Rethink building supplies. What does that mean? Can whoever...
Is that meant for the fire smart that was put out?
Does whoever said rethink building supplies want to say more about it? Not to put you on the spot, but to put you on the spot.
Or forest cover, what does that mean?
Or maybe add another.
If you got lots of wind, you better have a strong roof.
Yeah. I mean, this is actually, speaking about roofs, this is an example that's often used to talk about there's kind of like this relationship between future climate projections and resilience. So there's a famous example from Australia where a study showed that they studied what would happen if gusts increased. And with a 25% increase in gust speed, you were looking at like 6.5 times the building damage. And it was really literally just talking about homes and their roofs. And the adaptation for that is just putting the nails a little closer. It's very cheap. And so you don't really need the detailed wind projections to know that that's an adaptation you just want to start doing. It's cheap, it's easy, and it really protects you. They just happen to be designing right under that threshold, after which real extreme damage. Some of them things are not like that. So the one that I usually use is in a highly populated place like Metro Vancouver with stormwater management. If they're going to require bigger drainage pipes for these neighborhoods that have very expensive homes, you're talking about a lot of concrete. You're talking about millions of dollars if you just up your culvert size by one size. So you want to be sure that you're going to the right size, because if you guess too little, you may spend more money on your culvert and still have too much flooding. If you underestimate and have all this flooding. Yeah, scroll down. Are new ones coming at the bottom of this? Okay. Move to Mars. I mean, Elon Musk agrees with that one, so that's maybe not as silly as it sounds. Planting bananas.
Question for you, if you don't mind.
I don't know enough about bananas to know if or when that will work, but yeah.
So in a previous chart there, you showed us like millions of years ago, the temperature was already at what we're going to as business as usual. So what I'm wondering, as like a civilization, like who are we to say we can change the course of an Earth that's already been that warm without any industrial or human activity, and it was already that warm one day?
Yeah.
How can we change the course of what it's already experienced?
It's a good question. I've got a slide for that. I'll leave this up. Okay, so those are all those. I do have a question. I'm going to answer this question, and then I'm going to come back. You can keep answering that one that was up about solutions, but I'll open just to like general questions or feedback in case anyone wants to, quietly, anonymously send a question or feedback. But I'm going to answer that question. Okay. Take me a minute to find the slide. So hopefully, does this question interest everyone? Okay. If I can get it to come back to this. Okay, hold on. So I got to jump forward a bunch of slides. Okay, I think I found it. Bunch of orange lines should be coming up. Here we go. Okay. So this is a little bit technical, but I think it's interesting. So the climate models that provide all the projections we've been looking at, if you run them over the past and compare them, this is a way of checking that they're doing what we expect. This swath of orange lines is what you get if you include in the climate models all of the historical forcing. So things that drive our climate are the concentration of greenhouse gases, volcanoes. Volcanoes tend to cause cooling effect because they basically throw tiny little particles that reflect sunlight, and they last for a while. So volcanoes will show a cooling, but it's temporary. There's solar cycles in here, and that's pretty much everything. And so all of these same forcing factors, you can use these climate models. For my master's, what I did was modeled what the Earth was like 2.5 to 3.5 million years ago, and compared that to paleoclimate evidence and looked at how ocean circulation changed. And so the climate models will reproduce what happened millions of years ago. When you go back millions of years, you're also looking at orbital forcing. Over the scale of 100 years, wobbles in Earth's orbit don't play much of a role, but they're in there. They're just tiny. But that's one of the main things that's behind our glacial cycles. So there are all these natural cycles. But all of those things, those natural forcings, are all in here, in the climate models. And again, the climate models are basically, it's kind of like the same thing that Boeing would use when they're modeling flow over a wing and trying to design a wing that has better airflow. Except instead of modeling the flow of air over a wing, you're modeling these two fluids. Air is a fluid, it's just very low density fluid, and water in the ocean. And so you're modeling the entire planet's atmosphere and ocean and transfer of heat among all of those things. And so you have all of these wiggly lines. Any individual climate model run won't necessarily agree with a particular year. So you can see there's a spread here. There's like 30 or 40 different climate models. It's because the forcing is the same. But the greenhouse gas emissions don't constrain the climate that much, because you've probably heard this sort of butterfly effect, right? Butterfly flaps its wings and it causes a hurricane. That's how it's usually understood. That's not really what it means. It's not like a little flap from a butterfly's wing, if you followed that flap, eventually results in a hurricane. That is not what it means. What it means is if you had the perfect climate model, which is if we had access to parallel universes. We don't have those. The climate models are not perfect. But if you had a perfect climate model, you could start, you had access to a parallel universe. You started off with the exact same climate, and then you can actually measure what happens in these parallel universes. If these two parallel universes, the only difference between them is a butterfly flap in one spot. Eventually, 50 years later, in those climates, you'll have different hurricanes at different places. So Hurricane Katrina occurred in our version of Earth. This other parallel universe, Earth didn't have Hurricane Katrina, but the same number. If you had the same forcing in all of them, you'd have the same statistics of the weather. So you'd have the same number on average of hurricanes and the same strength. You just would have different ones occurring in different. Does that make any sense? So that's why you don't expect each of these individual traces to follow. But when you have a bunch of them, you're averaging out all of that natural variability on the year-to-year scale. So you do actually expect the average line to roughly follow what has happened in this one version, our climate model, which is the perfect climate model. And so then you can ask questions about how does, when we have volcanoes, do the climate models, all of them do get colder for a while. So that gives you a little bit of confidence that the climate models are doing the right thing. And so what happens if you take out greenhouse gas emissions and just hold constant at historical emissions? This is what the climate we would have had. And you can see there's just really no overlap between, so this still includes solar forcing, this includes volcanic forcing, and it just really doesn't overlap with that. Another way of kind of answering your question is that greenhouse gases do have, it's just the physics of how it works, they have this major of an effect. And in some ways, yes, we are talking about, in fact, I have a slide on this. We're talking about a couple of degrees, warming of a couple of degrees has happened before. But the last time, this isn't BC, this is global now, what I'm about to show when it comes up. So this is the change in greenhouse gas concentration in the last 150 years. It's actually higher than that now, but and so you see that amount of increase in greenhouse gases. When that happened in the past, it happened spread out over several thousand years, and it was associated with a temperature change of several degrees. It's the difference between several kilometers of ice over our heads here and today. So this is comparable to a similar kind of temperature difference. Is that? Yeah, and so I'm going to go back to, I'm going to open this up. So any other questions? Should I be brave and leave this up here? I guess I will. I mean, we all want to see Hermione still, I guess. But and I should mention, I didn't mention the particular links. So more information is our website. There's Climate Insights 101 is a great course that there's different modules on different parts of climate change that PICS, our sister organization, put together. And then the BCA Regional Adaptation Collaborative, which David also mentioned. There's a link to that there. And how are we for time? Oh, we're pretty much out of time. Data. I'm not sure if that's a question, but I think I'll take that as a compliment, I guess. What will we expect for future climate without human effects? We would expect the climate, without any human effects, we'd expect the climate of 1750, basically.
But like, is there a overall expectation of increase or decrease? Like, do we have any models for that had humans no effect? Or
I mean,
exist or something like that?
climate modelers do everything. There are climate modeling studies on, I was talking to somebody, was that yesterday? No, Friday about modeling 2.5 billion years ago, Earth, way far back. So yeah, I'm sure that exists. I don't know off the top of my head. They're actually very long. So one of the things that there's a whole area of research called detection and attribution. So that kind of thing where I showed that the blue line where we have all of the forcing except greenhouse gases, and it was different from the orange line where we have everything. There's a very formalized way of saying, well, statistically, how likely is the climate that has occurred to have happened even if greenhouse gases didn't influence the climate in the way that we know they do. And so, and you can come up with a number for that. And to do that work, you have to actually have very long runs of the climate models, like thousands of years under pre-industrial forcing. And so usually 1750 or 1850, for various reasons, are kind of taken as pre-industrial greenhouse gas concentrations. So there are thousands and thousands of years of that climate from climate models.
I guess I'm wondering is like, if we could take carbon capture to like another level, and could we go back to?
Oh yeah, sure, yeah. I don't know anything about.
From before now?
Yeah, so I say I don't know anything, but I don't know. I'm not an expert in geoengineering. There's a lot of stuff being discussed around. That's the sort of geoengineering. Usually there's sort of trade-offs. Like there are ways of doing geoengineering where you put sort of sulfur particles up in the atmosphere at high latitude or high altitudes in the atmosphere, which deals with the temperature because it reflects solar radiation, but it doesn't do anything for ocean acidification, which a lot of people get their food source from the ocean. So that would be we'd still have to deal with big species changes there. Is there climate change elsewhere in our solar system? Yes, that's actually one of the ways that we have very poor observations about climate change on other planets, but to the extent that we have those observations, you can run a climate model for Mars and compare it to what data we have for Mars, and yeah, it's just physics. So.
I understand that certain feedback mechanisms that were problematic for models. So, let's say with the warming climate at further northern latitudes and the melting of the permafrost, so then you're going to have enhanced release of methane and carbon and such. Are the models getting better at replicating that and incorporating those changes?
They are getting better at replicating that. So there's kind of the climate models. We get a new sort of set of climate model projections every 6 or 7 years. And that's the main difference between the projections I showed today and the ones from the 2015 reports. There's a newer set of climate models. And this newest set do include interactions between, so if climate change, they've always had albedo effects, but in terms of snow. But if you have this interaction between, as climate changes, do you cause vegetation to die that then releases more greenhouse gases? That is explicitly in the models now. There's, whether they're capturing it all or not is up for debate, but it's, that's on the order of tenths of a degree. It's not a major effect, and it is in there. What happens if wind gusts increase by 6? So this was wind gusts increased by 25%, and the damage increases by 6 times. Okay, well, we get to see more like this. Okay, cool. Well, is there something? Lots of trends. What are we going to see? Answers to the so what? Oh, yeah, that's the hard part. I don't know anything. I don't know.
I just want to respond to that comment. Do you think
Yeah.
the oil and gas industry is to blame as much as it's portrayed? I mean, that's a really, that's a real question. That comes to the heart of so many people. And I don't know if you want to answer that, but
Nope,
when I read that
sure don't.
question, I think that it's a societal issue. The oil and gas industry plays a role in the society which we all participate in. So I don't think when we're looking at the future, it's not so much about pointing fingers as reimagining the kind of society. Like oil and gas is responding to a need that exists. So that's more, I think, the way to frame that. That just when I felt that the emotion in that one, I wanted to
Yeah.
respond to it.
I mean, the area of solutions is not my expertise, but personally, I don't think blame is super helpful in general. So I'm more interested in sort of getting on with solutions rather than blame. But
Can you scroll down? There's a good question down below.
please scroll down. Why are we flipping from?
Further down, I think that there's one about mental health that I think is
Can I grow peaches here soon? I'm not sure when.
Yeah, right there.
Somebody studying
How accurate is climate data from northeastern BC in the 1950s? Not very. How do I manage my mental health? I'm losing my microphone. Yeah. Yes. Okay. Spiraled into climate change-related depression after Hurricane Harvey. I try to be optimistic. I don't know. It's just be matter of fact about. I mean, I do my own little part in helping. I think by showing what the future is going to be like. I don't know how people who carry the weight on their shoulders of trying to implement policies to reduce greenhouse gas emissions. I don't know how they deal with their mental health. I think that would be harder. So I'm not sure if that really answers that question.
Well, I don't think Mr. Trump is having a lot of problem with it. I would like to ask you whether, or if we continue the way we have been, how long before the Earth is basically uninhabitable for the species?
So it depends what you mean by uninhabitable. There are some papers that are starting to, there's some lines of research that are starting to ask this question, and it starts with, it's places in the Middle East mostly that start to become not conducive to human life for very many days of the year. So you start to get this, and yeah, you're looking towards the end of the century before places start. But I mean, you're having days. It's already occurring where we're having days in some parts of the world where it's not really conducive to human life, but it's like one day a year or every few years or something like that. So that's not uninhabitable. It's hard to live in.
Wasn't there a place, I think it was in South Africa, that like a town no longer has water, like the water sources dried up?
There's certainly individual places that are no longer habitable. I mean, the sort of most tangible version of that is from sea level rise, right? There are places that just are uninhabitable because of sea level rise. Not a concern here, of course, but places that are literally moving. Yeah. So what else? I think we're over time. I'm happy to stick around. I don't know if I'm happy to. Why is it targeting 2 degrees? Okay, so there's IPCC is working on a report of what 2 degrees looks like. So this question is being worked on. And why 2 degrees? Again, this is not the part that I'm expert in, but from where I sit, it's kind of, there's nothing magical about exactly that number, 2 degrees Celsius. It's just that it keeps us roughly, so 2 degrees globally is pretty close to that blue line that I showed. And that helps us avoid some of the more major impacts, especially the ecosystem, the sort of ecosystem type of collapse kind of impacts that are a lot harder to deal with than, your basements are flooding and roads are washing out, which is still a problem, but you can rebuild a road a little more easily than you can rebuild a species, right? So that 2 degrees Celsius is really meant to avoid some of the most catastrophic impacts of climate change, but it could be 2.1 Celsius or 1.9 or whatever. Some folks are arguing for 1.5, in fact. And I should mention, at the back, there is, what is your takeaway from tonight? Given the number of answers here, I'm not sure if one piece of paper will be enough there. But if folks want to, on their way out, just say a little bit about what you took away from tonight, I would love to have that. I think I will wrap up because I don't want to, if people are just sticking around late and are shy but really need to leave when we said we would end, I want to let you go. But I'll stick around and happy to chat one-on-one with folks who are interested. Thank you so much. Apologies to folks whose questions I didn't get to, but.